Max Planck's journey into the world of light began at a time when classical physics dominated the scientific landscape. In the late 19th century, scientists were exploring various aspects of radiation, but one particular puzzle eluded them: the problem of blackbody radiation. Blackbody radiation refers to the radiation emitted by an idealized object that absorbs all incoming light and emits radiation in a way that depends on its temperature. Classical theories, such as Rayleigh-Jean's law, had made predictions about the intensity of radiation emitted by black bodies at different wavelengths, but these predictions failed dramatically at higher frequencies. The predicted intensity of radiation grew infinitely as the wavelength decreased, which was referred to as the ultraviolet catastrophe. This anomaly posed a significant challenge to physicists and stood as a glaring contradiction in the otherwise successful framework of classical physics. At the heart of this issue was the behavior of light, which at the time was primarily understood in terms of wave theory. Classical physics, with its reliance on continuous energy exchanges, was unable to explain the observed patterns of radiation emitted by black bodies. The mathematical predictions based on the wave model did not match experimental results, especially in the ultraviolet range of the electromagnetic spectrum. It was clear that a new understanding of light, energy, and radiation was needed. Planck, at the time, was a young physicist working to solve this dilemma. Born in 1858 in Kiel, Germany, Planck had already established himself as a brilliant theoretical physicist by the time he began studying blackbody radiation. He had a deep appreciation for the complexities of thermodynamics and statistical mechanics, and he had been influenced by the works of renowned physicists such as Ludwig Boltzmann and Rudolf Clausius. These influences set the stage for his groundbreaking work. Planck's approach to understanding blackbody radiation, however, would not follow the conventional paths taken by his predecessors. Rather than relying purely on classical theories, he sought a solution that combined both experimental evidence and theoretical reasoning, and ultimately, his revolutionary thinking would break away from the existing paradigms. In 1900, Planck began working on the problem of blackbody radiation and developed an idea that would later become the cornerstone of quantum mechanics. To solve the problem, Planck introduced the concept of quantization of energy. He hypothesized that the energy of the oscillators inside a blackbody cavity could only take discrete values rather than continuous ones. In other words, rather than the oscillators having a continuous range of energy levels, their energy could only exist in specific increments, or quanta. This hypothesis was radical, as it defied the classical view that energy could vary smoothly and continuously. Planck's key insight came when he applied this quantization idea to the electromagnetic radiation emitted by a black body. He proposed that the energy of each oscillator inside the cavity was proportional to its frequency, and the energy was constrained to be an integer multiple of a fundamental unit. This unit of energy would come to be known as Planck's constant, symbolized by the letter h. The significance of Planck's constant was that it established a limit on how small the energy steps could be, and it was the first time in history that physicists had to acknowledge that energy could not be divided infinitely into smaller parts. The concept of quantization was completely foreign to classical physics, which had always assumed that energy could be infinitely subdivided. At first, Planck's ideas were met with resistance. The notion of quantization was difficult to accept, and Planck himself was initially hesitant to embrace it fully. He did not understand the full implications of his work, and he viewed the idea of quantum more as a mathematical trick to make the equations work, rather than a fundamental change in our understanding of physics. Nonetheless, Planck's formula for blackbody radiation, which incorporated the idea of quantization, turned out to match experimental data perfectly. This result was a breakthrough that could not be ignored. It not only solved the ultraviolet catastrophe but also hinted at the need for a new theory of physics, one that could explain the discrete nature of energy. The impact of Planck's work was not limited to just blackbody radiation. His discovery of energy quantization opened the door to a new way of thinking about energy in all physical systems. If energy could only be absorbed or emitted in discrete packets, this would have profound implications for many areas of physics, from atomic structure to the behavior of light. However, at the time, Planck's work was largely seen as a mathematical curiosity, and the broader consequences of his findings would not be fully realized until later. In the years following Planck's discovery, the world of physics underwent a dramatic transformation. Although Planck himself did not fully grasp the significance of his work, others would soon take his ideas further and develop the theory of quantum mechanics. One of the first scientists to build on Planck's work was Albert Einstein, who, in 1905, extended the concept of energy quantization to light. Einstein proposed that light itself could be thought of as discrete packets of energy, which he called photons. This idea, now known as the particle theory of light, would be a key step toward the development of quantum theory. In addition to Einstein, other physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would eventually use Planck's theories to develop the broader framework of quantum mechanics. These physicists built upon Planck's work by incorporating the notion of quantized energy levels into the study of atomic structure, the behavior of electrons, and the interactions between particles. Planck's work not only set the stage for the development of quantum mechanics, but it also had profound consequences for our understanding of the universe. The concept of quantization introduced by Planck changed how we viewed the universe at its most fundamental level. Planck's discovery helped physicists understand that at microscopic scales, the laws of classical physics no longer applied. Instead, the behavior of particles and energy was governed by a completely new set of rules that could only be understood through quantum mechanics. This shift in perspective would ultimately give rise to a new era in physics, one in which the boundaries of reality itself were stretched and challenged. As the years passed, Planck's contributions would be recognized as foundational to modern physics. In 1918, he was awarded the Nobel Prize in Physics for his work on blackbody radiation. Even though his quantum hypothesis was initially met with skepticism, his groundbreaking work would eventually lead to a profound shift in the scientific community's understanding of the universe. Planck's ideas would continue to inspire generations of physicists, and his legacy would be felt in a multitude of scientific fields, including materials science, electronics, and even the development of quantum computers. Max Planck's journey into the world of light was not just a quest to solve a specific scientific problem. It was a journey that led to the awakening of a new realm of physics. The world of light, energy, and matter had been forever altered by Planck's revolutionary ideas. His work not only solved the puzzle of blackbody radiation, but also opened up a whole new world of scientific discovery. Through his bold and innovative thinking, Planck changed the course of physics and left a legacy that continues to shape our understanding of the universe to this day. Max Planck's work on the quantization of energy brought about a profound shift in the way physicists understood the behavior of light and energy. The introduction of Planck's constant and the idea that energy could be emitted or absorbed in discrete packets challenged the prevailing classical theories of physics. This was not just a minor correction, it was the first step toward the development of a new and revolutionary field of physics, quantum mechanics. For many, the consequences of Planck's discovery were not immediately apparent. Planck himself had not fully grasped the enormity of his work, and in fact, he initially viewed his hypothesis as a mathematical trick. He believed that the introduction of quantization was a temporary solution to explain the behavior of blackbody radiation, not something that could be generalized to all forms of energy. However, as experiments continued to support Planck's findings, and as other physicists began to build on his ideas, it became clear that the implications of his work were far-reaching. Planck's concept of energy, quanta, did not just resolve the problem of blackbody radiation, it opened up entirely new questions about the nature of matter and energy. By proposing that energy could only exist in discrete units, Planck fundamentally challenged the classical view, which had held that energy could be varied continuously. The idea that energy was quantized meant that there were limitations on how much energy could be transferred, absorbed, or emitted at the atomic and subatomic levels. This concept led to the realization that classical physics could not fully explain the behavior of particles at very small scales. Planck's work marked the dawn of quantum mechanics, a new paradigm in physics. Planck's theories provided a necessary framework for understanding atomic phenomena. In the years that followed, his work inspired other scientists, most notably Albert Einstein. In 1905, Einstein extended Planck's concept of quantization to light itself, proposing that light was not just a wave, but also consisted of discrete packets of energy, which he called photons. This breakthrough was pivotal in understanding the photoelectric effect a phenomenon where light shining on a metal surface can cause the emission of electrons. Einstein's work built directly upon Planck's ideas, and in doing so, he laid the groundwork for the development of quantum theory. In addition to Einstein, several other notable physicists, including Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, expanded upon Planck's concept of quantization. Bohr, for instance, applied Planck's ideas to the atom, proposing that electrons orbit the nucleus in fixed energy levels. These energy levels were quantized, meaning that electrons could only exist in specific orbits and could only absorb or emit energy when they transitioned between these orbits. This work led to the development of the Bohr model of the atom, which explained the discrete spectral lines of elements. Heisenberg's uncertainty principle and Schrödinger's wave equation further refined the early ideas of quantum mechanics. These new developments helped solidify the theory that energy and matter at microscopic scales behaved in ways that were fundamentally different from the classical physics that governed larger systems. Schrödinger's wave equation, for example, showed that particles such as electrons could be described by wave functions, which gave probability for where an electron might be located in space, rather than definite positions as classical physics would have predicted. The birth of quantum mechanics, which was heavily influenced by Planck's work, had a number of far-reaching consequences. One of the most profound was the recognition that the universe operates on two different sets of rules. At large scales, classical physics, Newton's laws, thermodynamics, and electromagnetism still applied, but at microscopic scales, the rules of quantum mechanics took over, leading to behavior that defied everyday intuition. Light, for example, could behave both as a particle and a wave, depending on how it was observed. This duality, later encapsulated in the wave-particle duality of quantum theory, was one of the many puzzling aspects of the quantum world that scientists would struggle to understand for decades. Beyond the theoretical implications, the development of quantum mechanics also paved the way for a variety of technological innovation. The understanding of quantum behavior led to the development of technology such as semiconductors, which are the backbone of modern electronics. The invention of the laser, which relies on quantum principles, revolutionized fields ranging from telecommunications to medicine. Quantum mechanics also laid the groundwork for the development of quantum computing, a field that promises to revolutionize computing power by leveraging the strange and counterintuitive properties of quantum particles. As the field of quantum mechanics continued to evolve, Planck's role as its father became more evident. Without his initial insight into the quantization of energy, the subsequent development of quantum mechanics would have been impossible. His work fundamentally changed the course of physics, ushering in a new era where the strange and unpredictable behaviors of subatomic particles were not only accepted but studied in great detail. Planck's discovery reshaped our understanding of the universe and our place within it. However, it was not just in the realm of science and technology that Planck's legacy endured. His work also had philosophical implications. The idea that the universe operates according to laws that are not intuitive to human experience challenged long-held notions about determinism, causality, and reality itself. For centuries, physicists and philosophers had assumed that the universe operated in a predictable, deterministic fashion. The introduction of quantum mechanics, with its inherent uncertainties and probabilistic nature, forced scientists to reconsider these assumptions. In particular, Planck's constant, which had no physical explanation at the time, became a symbol of the fundamental limits of human knowledge. It represented a boundary to our understanding of the universe. Despite the remarkable success of quantum theory in explaining phenomena at small scales, it also highlighted the limits of what we can know. For example, Heisenberg's uncertainty principle revealed that there are limits to how precisely we can measure certain pairs of quantities, such as position and momentum, at the same time. This implied that there were inherent uncertainties in the very fabric of reality, and our ability to predict the future behavior of quantum systems was fundamentally limited. Even as quantum mechanics reshaped the scientific worldview, it left physicists with a sense of awe and mystery. Many of the early quantum pioneers, including Planck, were philosophical about the deeper implications of their work. They recognized that while quantum mechanics provided incredibly accurate predictions, it also challenged our basic understanding of reality. The quantum world, with its strange rules and paradoxical behaviors, seemed to offer more questions than answers. Yet, despite this uncertainty, Planck's work laid the foundation for a scientific revolution that would change the way humanity viewed the universe. In conclusion, Max Planck's work in the early 20th century ushered in a new era of scientific discovery and understanding. His quantum hypothesis and the introduction of Planck's constant marked the birth of quantum mechanics, a theory that would eventually reshape the entire field of physics. The implications of his discoveries were far-reaching, not only in science and technology but also in philosophy. The legacy of Planck's work continues to resonate in modern scientific endeavors, from the development of new technologies to the exploration of the fundamental nature of reality. Planck's contribution to the quantum awakening remains one of the most profound in the history of physics. The birth of Planck's quantum hypothesis marked the dawn of an entirely new way of thinking about the physical world. In 1900, when Max Planck first proposed his radical idea about the quantization of energy, the scientific community was deeply embedded in classical physics. The wave theory of light, developed by figures like James Clerk Maxwell, dominated the understanding of electromagnetic radiation. According to classical physics, energy could be emitted or absorbed in any arbitrary amount, which led to the puzzling problem of blackbody radiation. This phenomenon occurred when an idealized object, known as a blackbody, absorbed all incident light and then emitted radiation. The classical laws, based on the wave theory of light, predicted that the intensity of radiation would increase indefinitely as the wavelength decreased, creating what became known as the ultraviolet catastrophe. Classical theories were unable to explain this behavior accurately, and the problem seemed unsolvable until Max Planck entered the scene. Planck was not the first to be concerned with blackbody radiation, but his approach was different. While other scientists attempted to modify existing laws to accommodate the observations, Planck decided to take a different route altogether. Instead of assuming that energy could be emitted or absorbed continuously, he proposed that the energy levels of the oscillators inside a blackbody cavity could only take discrete, quantized values. In other words, Planck suggested that the energy of these oscillators was limited to specific units, or quanta, which could not be subdivided further. This bold idea would prove to be the key that unlocked the mysteries of black-body radiation and eventually laid the groundwork for quantum mechanics. At the time, Planck himself did not fully understand the implications of his hypothesis. He proposed the idea as a mathematical tool to solve the blackbody radiation problem, not as a fundamental shift in the nature of energy. The concept of quantized energy was so foreign to classical physics that Planck initially saw it more as a mathematical convenience than a revolutionary discovery. However, the formula he derived based on this assumption not only matched experimental results, but did so in a way that no classical theory could. This success led Planck to propose that energy, at its most fundamental level, could only exist in specific, indivisible packets. The smallest unit of energy in his theory came to be known as Planck's constant, symbolized by the letter. The introduction of Planck's constant was a game-changer. The constant itself was a fundamental property of nature, and it defined the smallest possible amount of energy that could exist at the quantum level. Its introduction meant that energy was not a continuous entity, but rather a discrete one. The significance of this idea was profound. It meant that the laws governing the microscopic world, where particles and energy behaved in ways that were previously unimaginable, were governed by entirely different rules than the laws that applied at larger scales. At the microscopic level, energy existed only in quantized packets, and the packets of energy would go on to become the cornerstone of quantum mechanics. Planck's work was, however, not fully appreciated at the time. His theory of quantization was seen as a curiosity, a mathematical trick to solve an immediate problem, rather than a fundamental shift in the way scientists should think about energy and matter. But the implications of his discovery would slowly unfold over time. While Planck himself remained unsure of the full importance of his work, his theories would eventually lead to the development of the broader field of quantum mechanics, which would fundamentally alter the landscape of physics. The concept of energy quantization had profound implications, particularly in the way scientists understood the behavior of light. For centuries, light had been treated primarily as a wave, but Planck's theory suggested that light could also behave as if it were made up of discrete particles, or quanta. This insight would later be developed further by Albert Einstein, who in 1905 expanded Planck's idea of quantization to light itself. Einstein proposed that light was composed of discrete packets of energy which he called photons. This was a revolutionary idea that would reshape the way scientists thought about the nature of light. Einstein's work on the photoelectric effect, which showed that light could cause electrons to be emitted from a metal surface, depended on the idea that light was quantized. According to Einstein, when light of a certain frequency struck a material, it imparted energy to electrons in discrete packets, or photons. The photoelectric effect was one of the first experimental confirmations of the particle nature of light, and a direct consequence of Planck's initial insight into quantized energy. Einstein's contribution to quantum theory helped establish the wave-particle duality of light, where light could exhibit both wave-like and particle-like properties depending on how it was observed. This duality would become one of the central concepts of quantum mechanics. In classical physics, light had been understood purely as a wave, as demonstrated by the work of Thomas Young and his double-slit experiment. However, with the advent of quantum theory, it became clear that light could also behave like a particle. This wave-particle duality, introduced by Planck and expanded by Einstein, became one of the foundational principles of quantum mechanics, laying the groundwork for future breakthroughs in physics. The consequences of Planck's quantum hypothesis were not limited to just the study of light. His idea of quantized energy also played a pivotal role in shaping the future of atomic theory. Niels Bohr, in particular, used Planck's concept of quantization to develop his model of the atom. Bohr proposed that electrons in atoms occupied fixed energy levels, and that they could only transition between these levels by absorbing or emitting a quantized amount of energy. Bohr's model explained the discrete spectral lines observed in atomic spectra, which classical theories had been unable to explain. The success of Bohr's model was a direct consequence of Planck's insight into the quantization of energy, and it marked the beginning of a new era in the study of atomic physics. The emergence of quantum theory marked a shift in the way scientists thought about the universe. Classical physics had operated under the assumption that the world was deterministic, that the future could be predicted based on the present. But quantum mechanics introduced an entirely new way of thinking, one in which particles and energy existed in probabilistic states. This uncertainty was famously captured by Werner Heisenberg's uncertainty principle, which stated that it was impossible to simultaneously know both the position and momentum of a particle with absolute precision. The probabilistic nature of quantum mechanics challenged long-held assumptions about the predictability of nature, and it forced scientists to confront the limits of human knowledge. Despite its counterintuitive nature, quantum mechanics quickly gained acceptance in the scientific community. The success of quantum mechanics in explaining phenomena at the microscopic scale was undeniable, and it led to the development of numerous technologies, from semiconductors and lasers to the nascent field of quantum computing. The principles of quantum mechanics continue to shape our understanding of the universe, influencing everything from the behavior of subatomic particles to the development of cutting-edge technologies. The legacy of Max Planck's quantum hypothesis is thus not just a theoretical contribution, it is a tangible, real-world influence that continues to affect our daily lives. In the decades following Planck's discovery, the field of quantum mechanics continued to grow and evolve. Physicists like Schrödinger, Heisenberg, and Dirac developed the mathematical framework that would form the foundation of quantum theory. The study of quantum systems led to the discovery of phenomena like quantum entanglement, which defied classical notions of locality and causality, and quantum tunneling, which made possible technologies such as tunnel diodes and scanning tunneling microscopes. As the field of quantum mechanics expanded, it opened up new frontiers of knowledge, some of which remain a mystery to this day. Max Planck's journey into the world of quantized energy, which began as an attempt to solve the problem of blackbody radiation, ultimately transformed the landscape of physics. Planck's quantum hypothesis laid the foundation for the development of quantum mechanics and forever changed our understanding of energy, matter, and the fundamental nature of the universe. Planck's contributions to science were not just confined to the study of radiation or atomic theory. They were the catalyst for a revolution in physics that continues to shape the scientific landscape today. His legacy, though not fully understood in his lifetime, has proven to be one of the most profound and lasting contributions to our understanding of the physical world. Through Planck's work, the quantum world was unveiled, and the nature of reality was forever altered. Max Planck's work on the quantization of energy began with a critical exploration into the mysterious world of blackbody radiation. Blackbodies, idealized objects that absorb all incoming radiation, emit radiation across a spectrum of wavelengths when heated. Classical physics had long struggled to explain the observed radiation patterns, especially at higher frequencies, which led to the infamous ultraviolet catastrophe predicted by the Rayleigh-Jeans law. According to this classical prediction, as the frequency of radiation increased, so did the intensity of emitted energy, ultimately tending toward infinity, an outcome that clearly contradicted experimental observation. Scientists were at an impasse, and it seemed that classical physics, which had so successfully described macroscopic phenomena, was inadequate at the microscopic level. Planck, however, approached the problem with a fresh perspective. He was aware of the limitations of classical physics and believed that a new model was necessary to account for the discrepancy. In 1900, rather than clinging to the wave model of light, which suggested that radiation could be emitted or absorbed continuously, Planck proposed the bold idea that the energy of radiation could only exist in discrete units or quanta. This was a dramatic break from classical thinking, which had assumed that energy could be smoothly and continuously distributed. Planck hypothesized that the oscillators in the walls of the blackbody cavity could only emit or absorb energy in fixed amounts, proportional to the frequency of the radiation. In essence, the energy of each oscillator in the blackbody cavity was restricted to discrete multiples of a fundamental unit of energy. Planck introduced what would later become known as Planck's constant, symbolized by the letter H, to describe this quantization of energy. The constant represented the smallest possible unit of energy transfer, marking a profound departure from the continuous energy spectrum envisioned by classical physics. By combining this hypothesis with existing thermodynamic principles, Planck was able to derive a mathematical formula for blackbody radiation that matched experimental results perfectly. This formula, known as Planck's law, provided a far more accurate prediction of blackbody radiation across all frequencies, and its success made Planck's hypothesis widely accepted by the scientific community, even though the full implications of his discovery were not yet understood. Planck's concept of energy quanta was, at first, met with skepticism by many of his peers. Even Planck himself was unsure of the full significance of his work. He viewed the quantization hypothesis as a mathematical convenience, a necessary step to solve a specific problem, rather than a fundamental law of nature. Planck was uncomfortable with the idea that energy was inherently quantized and hoped that it would be a temporary solution. However, as experimental data continued to support his theory, the importance of his work became undeniable. The idea that energy could be quantized laid the foundation for a new understanding of the microscopic world, and it would later serve as the cornerstone of quantum mechanics. The true significance of Planck's work would become evident only a few years later, when Albert Einstein extended Planck's concept of energy quantization to light. In 1905, Einstein published his paper on the photoelectric effect, in which he proposed that light itself was quantized. According to Einstein, light did not behave purely as a continuous wave, as had been assumed by classical physics, but instead consisted of discrete packets of energy called photons. The photoelectric effect, in which light striking a metal surface causes the emission of electrons, could not be explained by the classical wave theory of light. However, Einstein's proposal that light consisted of photons, each with an energy proportional to the frequency of the light, provided a straightforward explanation for the phenomenon. This groundbreaking work, building directly upon Planck's ideas, showed that energy and light were not just continuous waves, but also behaved as discrete particles. The concept of light as both a wave and a particle, known as wave-particle duality, would become one of the central themes of quantum mechanics. Einstein's work on the photoelectric effect showed that light could exhibit particle-like behavior under certain conditions, while Planck's quantization theory explained the behavior of radiation across a range of frequencies. The interplay between the wave and particle descriptions of light became a hallmark of quantum mechanics, which sought to reconcile these seemingly contradictory aspects of nature. Planck's initial work on the quantization of energy thus played a pivotal role in the development of wave-particle duality and in the broader understanding of light and matter. Niels Bohr one of the central figures in the development of quantum mechanics, also built upon Planck's ideas. In 1913, Bohr introduced his model of the atom, which applied Planck's concept of energy quantization to the behavior of electrons in atoms. According to Bohr's model, electrons did not spiral into the nucleus as classical physics would have predicted, but instead orbited the nucleus in discrete energy levels. Electrons could absorb or emit radiation only when they transitioned between these quantized energy levels. Bohr's model successfully explained the discrete spectral lines observed in hydrogen atomic spectrum, which had previously been a mystery to physicists. This was another important step in the evolution of quantum theory, and it directly owed its existence to Planck's insights into the quantization of energy. Planck's influence extended far beyond the work of Einstein and Bohr. Other physicists, such as Werner Heisenberg and Erwin Schrödinger, would continue to develop quantum mechanics into a comprehensive framework for understanding the microscopic world. Heisenberg's uncertainty principle, which stated that certain pairs of physical properties, such as position and momentum, could not be simultaneously known with absolute precision, introduced an inherent uncertainty into our understanding of the universe at the quantum level. Schrödinger's wave equation, which described the behavior of particles as wave functions, added a probabilistic element to the theory of quantum mechanics. Together, these developments further solidified the foundation that Planck had laid with his work on energy quantization. The birth of quantum mechanics was not just a theoretical shift, it also had profound practical implications. The understanding of quantum phenomena led to the development of technology such as semiconductors, lasers, and quantum computers. The advent of quantum mechanics revolutionized electronics, communications, and computing, paving the way for the digital age. Many of the technologies we take for granted today, from the microchips in our smartphones to the lasers in our CD players, rely on the principles of quantum mechanics that were first suggested by Planck's work. Quantum mechanics also had profound philosophical implications. It challenged the classical worldview, which had been shaped by the deterministic laws of Newtonian mechanics. The discovery of quantum indeterminacy, the idea that particles could exist in probabilistic state rather than fixed positions, forced scientists to reconsider the very nature of reality. The philosophical ramifications of quantum theory are still debated today, with questions about determinism, free will, and the nature of observation continuing to provoke discussion among physicists and philosophers alike. Despite its initially limited application, Planck's discovery of quantized energy levels had profound and far-reaching consequences. His introduction of Planck's constant, the smallest unit of energy, provided the foundation for a new understanding of the physical world. Planck's quantum hypothesis not only solved the blackbody radiation problem but also served as a launching point for the development of quantum mechanics. The theories that grew from his work not only expanded our understanding of the universe at its most fundamental level, but also led to groundbreaking technologies that continue to shape our modern world. The legacy of Max Planck is immense. His work laid the groundwork for one of the most important revolutions in the history of science. His contributions to the theory of quantized energy paved the way for the discovery that would shape our understanding of atomic and subatomic processes. Without Planck's pioneering insight, the development of quantum mechanics would not have been possible, and the world of science and technology would look very different today. Planck's work continues to inspire generations of scientists, and his legacy remains one of the most important in the history of physics. Max Planck's work on the quantization of energy fundamentally changed our understanding of the physical world. When Planck first ventured into the problem of blackbody radiation, he did so under the assumption that classical physics would be sufficient to explain it. However, when his equations began to conflict with experimental data, Planck found himself confronting the limitations of classical theories. Blackbody radiation, a concept rooted in thermodynamics and electromagnetism, had eluded scientists for decades. Classical physics predicted that as the frequency of radiation increased, the intensity would become infinitely large, which was an obvious contradiction to observed data, particularly in the ultraviolet range. This discrepancy became known as the ultraviolet catastrophe. In a world that was already comfortably operating under classical theories, this was a serious anomaly. The challenge to explain how blackbody radiation actually worked was one that had troubled many physicists for years. To address this, Planck proposed a bold hypothesis, the idea that energy was not continuous but quantized. This was a revolutionary shift in thinking, as classical physics assumed that energy could take any value. Planck argued that energy was emitted or absorbed in discrete packets, or quanta, and he introduced a mathematical formula that helped resolve the discrepancy. The formula provided a clear explanation for the observed radiation and was immediately successful in describing the behavior of black bodies across all frequencies. Although Planck's idea of quantized energy initially seemed like a mere mathematical trick, it set the stage for the birth of quantum mechanics, which would forever change how we understand the universe. What Planck had uncovered was the deep-rooted connection between energy and frequency in a fundamentally new way. His insight showed that energy was proportional to the frequency of the radiation, with the proportionality constant now known as Planck's constant, symbolized by H. This constant, which would later be recognized as a fundamental feature of nature, represented the smallest possible unit of energy transfer. It marked the beginning of a new understanding of the relationship between light, energy, and matter, one that was vastly different from the continuous exchange of energy assumed by classical mechanics. This change in perspective laid the groundwork for future developments in physics, and Planck's constant soon became one of the most significant constants in science. It was Planck's groundbreaking idea that revealed the need for a new model of physics, one in which the laws governing the microscopic world were not the same as those governing the macroscopic world. Planck's hypothesis of quantized energy challenged the long-standing classical theories and brought into focus the idea that the universe was governed by discrete, rather than continuous principles, setting the stage for the quantum revolution. The introduction of Planck's quantum hypothesis had consequences that extended far beyond the field of blackbody radiation. One of the most important implications of Planck's theory was its profound effect on the development of the atomic model. At the time, the atom was understood through the lens of classical physics, which described electrons moving in circular orbits around a nucleus. However, this model did not explain several key observations, such as the discrete spectral lines produced by atoms when heated. Classical physics predicted that electrons would emit continuous radiation as they moved in orbits, yet experimental data showed that only specific wavelengths of light were emitted, forming a distinct set of spectral lines. It was Niels Bohr, building upon Planck's work, who proposed a new model of the atom. Bohr suggested that electrons and atoms do not move in arbitrary orbits, but are instead confined to discrete energy levels. These energy levels were quantized, meaning electrons could only exist in specific, fixed orbits around the nucleus. The transitions between these orbits could only occur by absorbing or emitting discrete amounts of energy corresponding to the difference between these fixed levels. Bohr's atomic model successfully explained the discrete spectral lines observed in hydrogen and other atoms, providing a much-needed breakthrough in atomic physics. Bohr's model of the atom, while groundbreaking, was only one of the early fruits of Planck's idea of quantization. The theory of quantization would later evolve into a broader framework, which would eventually be known as quantum mechanics. This new field of physics would change not just atomic theory, but the entire way we view the physical universe, from the behavior of subatomic particles to the largest scales of cosmology. The transition from classical physics to quantum mechanics was not an easy one, and many physicists initially resisted the idea that the universe was governed by probabilistic, discrete laws. However, as more experimental evidence accumulated, the new quantum view of reality became the accepted framework for understanding the behavior of the atomic and subatomic worlds. The concept of quantized energy, introduced by Planck, also had profound implications for our understanding of light itself. Before Planck, light was generally treated as a continuous wave as described by the electromagnetic wave theory proposed by James Clerk Maxwell. According to this theory, light and other forms of electromagnetic radiation were seen as oscillation of electric and magnetic fields that propagated through space in continuous waves. However, Planck's introduction of the concept of energy quanta challenged the idea that light could be purely a wave. Instead, light began to be understood as a combination of both wave-like and particle-like properties, leading to the development of the theory of wave-particle duality. In 1905, Albert Einstein expanded on Planck's work by proposing that light which had long been considered a wave, also had particle-like properties. He suggested that light could be thought of as being composed of discrete packets of energy, which he called photons. This explanation helped to resolve the long-standing puzzle of the photoelectric effect, in which light striking a metal surface caused the emission of electrons. Classical wave theory could not explain this phenomenon, but Einstein's idea that light consisted of quanta, or photons, provided the necessary explanation. The energy of each photon was proportional to the frequency of the light, which was directly derived from Planck's quantization hypothesis. Einstein's work on the photoelectric effect helped to solidify the idea that light exhibited both wave-like and particle-like properties, a concept that would become known as wave-particle duality. This idea would be further developed by other physicists, such as Louis de Broglie and Werner Heisenberg, who extended the concept of wave-particle duality to matter. De Broglie proposed that particles, such as electrons, also exhibited wave-like properties, and Heisenberg developed the uncertainty principle, which stated that there were fundamental limits to how precisely we could measure certain pairs of quantities, such as position and momentum, at the same time. The wave-particle duality of light and matter became one of the most important ideas in the field of quantum mechanics. The wave-particle duality of light was a key feature of the new quantum theory, which would eventually revolutionize our understanding of the microcosm. Quantum mechanics explained phenomena that classical physics could not, such as the behavior of particles at the atomic and subatomic levels. It showed that the microscopic world was governed by probabilistic laws rather than deterministic ones, and that particles could exist in multiple states at once, only deciding on a particular state when observed. These ideas, which seemed completely alien to the classical understanding of reality, would change the course of physics forever. Despite the revolutionary nature of Planck's work, it would take decades for the full implications of his ideas to be realized. His theory of energy quantization, initially a mere mathematical tool, would evolve into the foundation of an entire field of physics. Planck's constant, once viewed as a mathematical curiosity, became one of the most important constants in the physical sciences. It would serve as the cornerstone of quantum mechanics, influencing everything from the behavior of particles to the development of new technologies. In addition to its impact on science, Planck's work also had philosophical consequences. Quantum mechanics challenged the deterministic worldview that had been the basis of classical physics. The new theory introduced the idea of uncertainty and probability at the most fundamental level of nature, suggesting that the universe at its smallest scales was unpredictable and governed by chance. This departure from classical determinism was difficult for many to accept, and it sparked heated debates about the nature of reality and the limits of human knowledge. Planck's work forced scientists to rethink their understanding of the universe and to accept that at the most fundamental level, nature might not be as predictable as it had once seemed. Planck's contributions to science and physics were immense, but his legacy extends beyond the realm of pure theory. His work laid the groundwork for the development of numerous technologies that have transformed our world, from semiconductors to lasers to quantum computers. The understanding of quantum phenomena has led to innovations that have shaped modern life in ways that were unimaginable in Planck's time. His theory of quantized energy was not just a theoretical breakthrough, it was the key to unlocking a new era of scientific and technological progress. Max Planck's work, though initially met with skepticism, became one of the most important breakthroughs in the history of physics. His quantization hypothesis, which solved the problem of blackbody radiation, was the spark that ignited the quantum revolution. Today, quantum mechanics is one of the most successful theories in physics, underpinning much of modern technology and our understanding of the universe. Planck's legacy, both as a scientist and as a philosopher, continues to shape the way we think about the world, and his contributions remain as relevant today as they were over a century ago. Max Planck's quantum hypothesis, which revolutionized physics, led to a complete rethinking of the nature of energy, light, and the universe itself. It is hard to overstate the significance of Planck's discovery, for his hypothesis provided the first clear understanding of black-body radiation, solved one of the greatest dilemmas in physics at the time, and opened the doors to the quantum mechanical world. Although the ideas Planck introduced seemed almost incomprehensible at first, they were eventually embraced as the bedrock of quantum theory, a framework that would evolve to explain the most fundamental aspects of nature. The scientific community in the late 19th century had already confronted a number of issues that classical physics could not adequately address. The phenomenon of blackbody radiation was one of these problems. A blackbody is an idealized object that absorbs all incident radiation and emits radiation based on its temperature. Classical physics, grounded in the principles of continuous energy, suggested that as the temperature of a black body increased, it would emit radiation at higher and higher frequencies, particularly in the ultraviolet range. However, the predictions of classical physics led to an infinite increase in the intensity of radiation as the frequency approached infinity, creating the ultraviolet catastrophe, which was a stark contradiction to experimental observation. This contradiction was so severe that it challenged the very foundations of classical physics. It seemed as though the laws of physics were incomplete, as they failed to explain the most basic phenomenon of radiation. The need for a new model, one that could accommodate these discrepancies, was clear. Planck, in his work on blackbody radiation, addressed this issue in a way that would forever alter the scientific landscape. Planck suggested a radical idea. Rather than assuming that energy could be emitted or absorbed continuously, he proposed that energy could only exist in discrete amounts, or quanta. In his view, energy could not be transferred in arbitrary amounts, but in fixed multiples of a fundamental unit. At first, Planck did not fully grasp the full significance of this idea. He introduced quantization as a mathematical convenience, a necessary assumption to solve the blackbody radiation problem. But this seemingly small change led to a cascade of discoveries that would reshape the course of physics. Planck derived a formula for blackbody radiation that perfectly matched the experimental results, and his success was immediately evident. The introduction of Planck's constant, which became the symbol h, was central to this formula and would later be understood as a key constant of nature, fundamental to the workings of the quantum world. Planck's work was revolutionary, but it was not immediately accepted as the beginning of a new era in physics. At first, Planck himself was not convinced that his hypothesis represented a fundamental shift in the understanding of the universe. For him, the quantization of energy was simply a mathematical tool that allowed him to solve an immediate problem. In fact, Planck continued to believe that classical physics would eventually be able to explain all phenomena. However, as other physicists began to work with his idea of quantization, the true implications of his discovery began to unfold. One of the most significant developments was the work of Albert Einstein, who, in 1905, extended Planck's idea of quantized energy to light itself. Einstein proposed that light was not just a continuous wave, as had been traditionally assumed, but was made up of discrete packets of energy, which he called photons. This was a groundbreaking insight because it provided an explanation for the photoelectric effect, a phenomenon that classical wave theory could not account for. In the photoelectric effect, light shining on a metal surface causes the emission of electrons, but the behavior of light in this context could not be explained by wave theory alone. Einstein's photon hypothesis, based on Planck's concept of quantized energy, provided the key to understanding the photoelectric effect. In doing so, it confirmed that energy could be transferred in discrete packets and light could behave both as a wave and a particle. Einstein's work on the photoelectric effect, which earned him the Nobel Prize in Physics in 1921, further solidified Planck's contribution to quantum mechanics. Einstein's breakthrough would lay the groundwork for the development of the broader framework of quantum theory, which would eventually include contributions from Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. These physicists built on Planck's idea of quantized energy, eventually developing a new theory that described the behavior of matter and energy at the atomic and subatomic scales. Planck's influence on quantum mechanics was profound. Without his initial insight into the quantization of energy, the subsequent developments in quantum theory would not have been possible. The most important implication of Planck's work was its fundamental departure from the classical worldview. In classical physics, energy was assumed to be continuous, meaning that it could take on any value. Planck's hypothesis, by contrast, suggested that energy was not continuous but existed in discrete amounts. This shift from continuity to quantization marked a pivotal moment in the history of physics, as it signaled the need for a new model to explain the workings of the universe. The implications of quantization extended far beyond blackbody radiation. If energy were quantized, this meant that many of the assumptions that had guided physics for centuries would no longer hold. The universe, at the microscopic level, was governed by fundamental different rules than those that applied at the macroscopic scale. As quantum mechanics developed, it became clear that the new theory was not just an incremental improvement on classical physics but a radical rethinking of the very nature of reality. At the quantum level, particles did not behave in the deterministic, predictable manner that classical mechanics had described. Instead, quantum mechanics introduced the concept of probability. Particles, like electrons, existed in probabilistic states, meaning their position and momentum could not be precisely determined at the same time, as evidenced by Heisenberg's uncertainty principle. The probabilistic nature of quantum mechanics stood in stark contrast to the deterministic world of classical physics. As quantum theory expanded, the work of Planck, Einstein, and others led to the development of technologies that were previously unimaginable. The understanding of quantum phenomena gave rise to the field of quantum electronics, which led to the invention of devices like the transistor and the laser. These inventions revolutionized electronics and communication, creating the foundation for the digital age. The understanding of quantum mechanics also paved the way for the development of quantum computing, which promised to revolutionize the world of computation by harnessing the strange properties of quantum systems. The quantum revolution, which began with Planck's hypothesis in 1900, has continued to influence nearly every aspect of modern technology. Beyond its technological applications, quantum mechanics also has deep philosophical implications. The probabilistic nature of quantum theory challenges classical notions of determinism, raising questions about the predictability of the universe and the nature of reality. The famous thought experiments of physicists like Schrödinger, who envisioned a cat in a box that could be both alive, dead until observed, have sparked debates about the role of the observer in determining the outcome of quantum events. The strange and counterintuitive aspects of quantum mechanics, such as superposition and entanglement, continue to defy our everyday understanding of reality. Yet, despite its paradoxes and mysteries, quantum mechanics remains one of the most successful theories in the history of science, explaining everything from the behavior of particles to the formation of stars. Max Planck's legacy is immense. His work on the quantization of energy set the stage for one of the most profound shifts in scientific thinking. His constant, Planck's constant, would become a fundamental feature of the quantum world, guiding scientists in their exploration of atomic and subatomic phenomena. While Planck did not live to see the full implications of his work, his ideas would eventually reshape the entire field of physics. Quantum mechanics would evolve from Planck's initial hypothesis into a powerful tool for understanding the fundamental workings of the universe. Today, the world of quantum physics continues to expand, and Max Planck's ideas remain at the heart of scientific exploration. Through his work, Max Planck not only solved the blackbody radiation problem, but also unlocked the door to a new realm of physics. His theory of quantized energy laid the foundation for the development of quantum mechanics, which would go on to explain the behavior of light, matter, and energy at the most fundamental level. Planck's legacy, both as a scientist and as a philosopher, continues to shape our understanding of the universe. His contributions remain one of the most profound and lasting in the history of science, and his ideas will continue to inspire future generations of physicists, engineers, and thinkers. Max Planck's work on quantization not only resolved the issue of black-body radiation but also laid the foundation for a new era in physics. His quantum hypothesis, initially seen as a mathematical tool, would evolve into the very heart of quantum mechanics, an entirely new framework for understanding the behavior of energy, light, and matter at the microscopic scale. The quantum leap, sparked by Planck's ideas, transcended blackbody radiation, shaping the future of science and technology in profound ways. One of the key elements of Planck's work was the introduction of Planck's constant, a fundamental constant in nature that defined the smallest unit of energy that could be transferred. The idea of quantization represented a departure from the classical physics model, where energy was believed to be continuous. By postulating that energy could only exist in discrete packets, Planck's work revolutionized our understanding of how energy is absorbed and emitted. This allowed for a new way of approaching energy phenomena that had previously defied classical explanation. Planck's constant, denoted as h, would become one of the most important constants in physics, playing a crucial role in subsequent theories such as Heisenberg's uncertainty principle and Schrödinger's wave mechanics. The concept of quantization also introduced a paradigm shift in the way scientists understood light. Prior to Planck's work, light had been understood in terms of its wave property, and the idea of light as a particle was far from the scientific mainstream. Planck's insight, however, that energy emitted or absorbed by an oscillator could only exist in multiples of a Bay energy unit, laid the groundwork for the later development of the photon theory of light by Albert Einstein. Einstein's work on the photoelectric effect in 1905 directly built on Planck's quantization hypothesis, suggesting that light could indeed behave like particles, photons, which carry energy. This concept would later become central to the field of quantum mechanics, where particles and waves could coexist as complementary aspects of reality, a notion that would come to be known as wave-particle duality. In addition to its implications for energy and light, Planck's theory had a profound impact on the development of atomic physics. One of the major hurdles in atomic theory at the time was the inability of classical physics to explain why atoms emitted only specific wavelengths of light, or why electrons appeared to occupy discrete orbits in the atom. Niels Bohr, in his model of the atom, incorporated Planck's idea of quantized energy levels to explain these observations. Bohr suggested that electrons in atoms could only exist in fixed orbits with specific energies, and when they moved between these orbits, they emitted or absorbed quantized amounts of energy. This model not only explained the spectral lines of hydrogen, but also opened the door for a deeper understanding of atomic structure and the forces that govern it. Lastly, Planck's ideas contributed to the philosophical underpinnings of the emerging field of quantum mechanics. The introduction of quantized energy and the consequent departure from the determinism of classical physics meant that scientists were forced to reconsider their understanding of reality itself. Planck's work implied that the universe, at its most fundamental level, was governed by principles of probability and uncertainty, rather than certainty and determinism. This was most famously encapsulated in Werner Heisenberg's uncertainty principle, which states that it is impossible to know both the position and momentum of a particle with absolute precision at the same time. These new principles undermined the classical belief in a fully deterministic universe, replacing it with the more probabilistic and uncertain view of reality. The quantum theory introduced by Planck would go on to transform not only the way we understand the natural world, but also the technological landscape. The quantum revolution led to the development of semiconductors, lasers, and quantum computing, and continues to shape fields like materials science, cryptography, and artificial intelligence. The profound influence of Planck's work reaches far beyond the laboratory, impacting everyday technology and the modern digital world. Planck's legacy, both in terms of his theoretical contributions and their practical applications, continues to resonate across multiple disciplines, cementing his place as one of the most significant figures in the history of science. Max Planck's revolutionary concept of quantization became the cornerstone of modern physics, marking a turning point in how energy and light were understood. Planck's ideas transformed not only the field of physics, but also our technological landscape. His introduction of Planck's constant and the notion that energy could only exist in discrete units rather than as a continuous flow led to the birth of quantum mechanics. Although initially used to address the blackbody radiation problem, Planck's work ultimately unlocked the door to an entirely new realm of scientific exploration. One of the most profound consequences of Planck's hypothesis was the introduction of Planck's constant, symbolized by h. This constant became a fundamental feature of quantum theory and defined the smallest possible quantum of energy. Its discovery was crucial because it represented the boundary between classical and quantum physics. In classical physics, energy was assumed to be continuous, allowing for any value to be taken by a system. Planck's constant established a limit. Energy could only change in fixed increments, not continuously, fundamentally altering how scientists approached energy and radiation. The constant became central to later theories, from Einstein's photoelectric effect to the development of quantum mechanics, acting as a guidepost for future generations of physicists. Without this essential constant, the formulation of quantum mechanics would not have been possible, and much of modern technology would not exist. The implications of Planck's idea extended far beyond blackbody radiation and energy quantization. Planck's theory directly impacted the understanding of light itself. Prior to Planck, light was primarily treated as a wave phenomenon as per the wave theory proposed by Maxwell. This view was dominant, and light was thought to be a continuous wave. Planck's insight into the quantization of energy led to the idea that light, too, could be thought of as quantized, consisting of discrete energy packets known as photons. This radical shift in thinking was further explored by Albert Einstein, who applied Planck's ideas to explain the photoelectric effect, wherein light striking a metal surface caused the emission of electrons. Classical wave theory could not explain this behavior, but by treating light as quanta, Einstein showed how it could be modeled as a particle, fundamentally changing the way light was understood. Einstein's work on the photoelectric effect, which earned him the Nobel Prize in Physics, built directly upon Planck's ideas and was a crucial step in the development of quantum mechanics. In addition to advancing the understanding of light, Planck's theories also had a lasting impact on atomic theory. Prior to Planck, the atom was described using classical mechanics, which struggled to explain the discrete nature of atomic spectra. Classical physics predicted that electrons should spiral into the nucleus, losing energy continuously. However, this did not match observed atomic behavior, where electrons occupied specific energy levels and emitted or absorbed only discrete amounts of energy when transitioning between these levels. Niels Bohr, building on Planck's work, proposed a model of the atom in which electrons moved in specific orbits around the nucleus, each with a fixed energy. When electrons jumped between these orbits, they would emit or absorb energy in discrete quanta. This model successfully explained the discrete spectral lines seen in hydrogen and other atoms, providing the first comprehensive understanding of atomic structure. Without Planck's concept of quantized energy, Bohr's atomic model would have been impossible. Beyond its contributions to atomic theory, Planck's work also led to an entirely new way of thinking about the nature of reality itself. Quantum mechanics, the framework that arose from Planck's ideas, introduced uncertainty and probability into the equation, replacing the deterministic universe of classical mechanics with one that was inherently unpredictable at the microscopic level. Heisenberg's uncertainty principle, a key concept in quantum mechanics, emerged from Planck's quantization hypothesis. The uncertainty principle states that it is impossible to simultaneously know both the exact position and momentum of a particle. This introduced a radical shift in the philosophy of science, suggesting that the universe at the quantum level could not be fully understood in deterministic terms. Instead, it was governed by probabilities, where outcomes could only be predicted with a certain level of certainty, not absolute precision. The ripple effects of Planck's work were not limited to the abstract world of theoretical physics, but extended into practical, real-world technologies. Planck's quantum mechanics laid the foundation for the development of technologies such as semiconductors, lasers, and quantum computers, all of which are integral to modern technology. The advent of semiconductors revolutionized electronics and gave birth to the computer age, while the invention of lasers transformed fields as diverse as medicine, telecommunications, and entertainment. Quantum mechanics has also paved the way for emerging fields like quantum computing and quantum cryptography, technologies that promise to redefine computing power and security in the coming decades. Planck's ideas have, in essence, shaped the technological infrastructure of the modern world and continue to fuel innovation in countless industries. In sum, Planck's contributions to science were not just confined to the development of quantum mechanics, but extended to nearly every aspect of modern science and technology. His introduction of energy quantization and Planck's constant fundamentally shifted our understanding of the physical world, laying the groundwork for future discoveries. Quantum mechanics, which emerged from Planck's theories, continues to shape the future of science and technology, driving advancements in fields as varied as computing, telecommunications, and medicine. Max Planck's work did more than solve a specific scientific problem. It ignited a revolution that would change the course of physics and human knowledge forever. Max Planck's contributions to physics fundamentally reshaped the way we understand the universe, starting with his revolutionary work on the quantization of energy. In 1900, when Planck first introduced his quantum hypothesis, he was trying to solve the long-standing problem of blackbody radiation. Classical physics was unable to explain the observed behavior of blackbody radiation, which led to a contradiction known as the ultraviolet catastrophe. Classical models predicted that as the temperature of an object increased, the intensity of radiation emitted by that object would increase indefinitely at shorter wavelengths, specifically in the ultraviolet range. However, experiments showed that the intensity actually began to decrease at high frequencies. Planck's genius was in recognizing that the solution lay in fundamentally changing how we think about energy. Planck's hypothesis was that energy is not continuous, as classical physics had assumed, but is quantized. This meant that energy could only exist in discrete amounts, or quanta, and could not be subdivided into smaller units. To explain this, Planck introduced a new constant now known as Planck's constant, which represented the smallest possible energy unit. By incorporating this constant into his equation for blackbody radiation, he derived a formula that perfectly matched experimental data across all frequencies. While Planck initially viewed his quantization theory as a mathematical trick to solve the blackbody radiation problem, it soon became clear that this idea was far more profound and would become the cornerstone of quantum mechanics. One of the most groundbreaking implications of Planck's work was the introduction of Planck's constant, symbolized as this constant became a fundamental feature of quantum theory, serving as a bridge between the microscopic world of atoms and the macroscopic world we observe. Planck's constant became central to understanding the discrete nature of energy and the interaction between light and matter. In the years following Planck's discovery, this constant would be used in numerous developments across quantum mechanics, from the understanding of atomic structure to the development of technologies like semiconductors and lasers. Planck's constant essentially marked the boundary between the classical and quantum worlds, signaling the emergence of a new era in physics. Planck's concept of quantization did not just explain blackbody radiation, it also had a profound impact on the way light itself was understood. Prior to Planck's work, light was primarily thought to be a continuous wave, as described by the electromagnetic theory of James Clerk Maxwell. However, Planck's introduction of energy quanta suggested that light could also behave as discrete packets of energy. This was a crucial step toward understanding the photoelectric effect, which could not be explained by classical wave theory. In 1905, Albert Einstein built on Planck's idea by proposing that light is made up of particles, or photons, each with energy proportional to its frequency. Einstein's work on the photoelectric effect provided experimental evidence for Planck's quantization theory and earned him the Nobel Prize in Physics. This particle-like behavior of light, which was later encapsulated in the wave-particle duality, remains a fundamental concept in quantum mechanics. In addition to its implications for light, Planck's work also had a significant impact on the development of atomic theory. Before Planck's theory, the behavior of atoms and their emission spectra could not be explained by classical physics. In particular, the discrete lines observed in atomic spectra were a mystery. Niels Bohr, in 1913, built upon Planck's idea of quantization and proposed that electrons in atoms could only occupy certain discrete energy levels. When electrons transitioned between these levels, they emitted or absorbed quantized amounts of energy. Bohr's model of the atom successfully explained the spectral lines of hydrogen, and it was a direct consequence of Planck's insight into the quantization of energy. This marked the beginning of a new chapter in atomic theory, where energy levels were not continuous but discrete, with profound implications for our understanding of matter. Another important consequence of Planck's discovery was the shift in how scientists understood the nature of reality itself. Classical physics was built on the idea of determinism, where the future could be predicted with absolute certainty if the present conditions were known. However, Planck's theory and the quantum mechanics that followed introduced an element of uncertainty into our understanding of the universe. Werner Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, stated that it is impossible to simultaneously know the exact position and momentum of a particle with absolute precision. This uncertainty was not a limitation of measurement tools, but a fundamental feature of nature. The probabilistic nature of quantum mechanics contradicted the deterministic worldview of classical physics, forcing physicists to accept that the universe at the smallest scales is inherently uncertain and unpredictable. The development of quantum mechanics, beginning with Planck's work, not only altered the way we understand the universe at a fundamental level, but also revolutionized technology. The understanding of quantum behavior led to the invention of semiconductors, which formed the basis of modern electronics, including everything from computers to smartphones. The development of lasers, which relies on the principles of quantum mechanics, has had a profound impact on fields ranging from telecommunications to medical technology. In recent years, quantum mechanics has led to the exploration of quantum computing, a field that promises to revolutionize the way we process information. Quantum technologies continue to shape the modern world in ways that would have been unimaginable at the time of Planck's original work. Max Planck's work on the quantization of energy, though initially met with skepticism, became one of the most influential discoveries in the history of physics. His theory set the stage for the development of quantum mechanics, which transformed our understanding of energy, light, and matter. Planck's constant remains a key feature of quantum theory, and his ideas continue to shape not only theoretical physics, but also a wide range of technologies that impact our daily lives. His legacy is one of the most profound in the history of science, and his work continues to inspire generations of physicists exploring the mysteries of the quantum world. Planck's contributions, which began with the quantization of energy, ultimately reshaped the very fabric of science, paving the way for an era of discovery that would change the course of human history. Max Planck's groundbreaking theory of quantization revolutionized our understanding of energy and light, reshaping the future of physics. His work on blackbody radiation addressed a long-standing problem that classical physics could not solve. Classical physics had predicted that the intensity of radiation emitted by a blackbody would continue to increase indefinitely as the wavelength decreased, leading to the ultraviolet catastrophe. This paradox indicated that classical theories were incomplete, as they failed to match experimental data. To solve this issue, Planck introduced the radical idea that energy was not continuous, but rather quantized, existing in discrete packets. This simple yet revolutionary hypothesis would later form the bedrock of quantum mechanics. Planck's hypothesis involved the idea that energy could only be emitted or absorbed in fixed amounts, which he referred to as quanta. This assumption was essential in solving the blackbody radiation problem. By introducing a fundamental constant, now known as Planck's constant, denoted, he established the smallest possible unit of energy transfer. Planck's constant was critical in describing the relationship between energy and frequency. This discovery provided a solution to the ultraviolet catastrophe and marked the beginning of a new era in physics. Though initially seen as a mathematical trick, Planck's theory was later recognized as a profound shift in how we understood the behavior of energy and light, initiating the quantum revolution. One of the most important consequences of Planck's discovery was the idea that energy is not continuous but instead exists in discrete units. This shift had a major impact on our understanding of light. For centuries, light was treated purely as a wave phenomenon. Following the electromagnetic theory of light developed by James Clerk Maxwell. However, Planck's work led to the concept that light, too, could behave as a particle. This insight was pivotal in the later development of the photon theory of light by Albert Einstein. In 1905, Einstein extended Planck's quantization theory to explain the photoelectric effect, showing that light could be thought of as consisting of discrete packets of energy which he called photons. This explanation was groundbreaking and provided experimental evidence for the quantum theory of light, establishing light as having both wave-like and particle-like properties. Planck's work also influenced the development of atomic theory. Classical models of the atom, such as those proposed by J.J. Thomson and Ernest Rutherford, were based on the assumption that electrons orbited the nucleus in continuous orbits. However, these models could not explain the discrete lines in atomic spectra. Niels Bohr, building on Planck's quantization concept, introduced his model of the atom in 1913. Bohr proposed that electrons in atoms occupy specific, quantized energy levels, and transition between these levels correspond to the absorption or emission of discrete amounts of energy. This model successfully explained the spectral lines of hydrogen and was a major step in the development of modern atomic theory. The impact of Planck's work on atomic theory did not end with Bohr. His ideas also influenced the development of quantum mechanics, a new framework for understanding the behavior of matter at the smallest scales. Werner Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics, was rooted in Planck's quantization concept. Heisenberg's principle states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This uncertainty introduced a probabilistic element to the study of particles, contrasting sharply with the deterministic views of classical physics. Quantum mechanics, which grew out of Planck's work, would ultimately replace classical physics as the framework for understanding the subatomic world. Planck's work also had far-reaching philosophical implications. Classical physics was based on a deterministic view of the universe where the future could be predicted from the present state of a system. However, quantum mechanics, with its inherent uncertainty and probabilistic nature, challenged this view. The recognition that the universe at its most fundamental level is governed by chance rather than certainty forced scientists to reconsider the nature of reality. This shift not only had profound implications for physics but also sparked philosophical debates about the nature of observation, measurement, and the limits of human knowledge. Quantum mechanics suggested that reality at the microscopic level is not fully determined until it is observed, raising questions about the role of consciousness in shaping the universe. The legacy of Planck's work extends far beyond the realm of theoretical physics. His concept of energy quantization paved the way for the development of numerous technologies that have transformed modern society. The advent of quantum mechanics enabled the invention of the semiconductor, the laser, and the transistor, all of which are central to today's electronics and information technology. The development of these technologies has led to the proliferation of computers, smartphones, and other electronic devices that have become an essential part of daily life. In recent years, quantum mechanics has also given rise to the field of quantum computing, which promises to revolutionize computing power by harnessing the strange properties of quantum systems. Planck's influence on technology is thus far-reaching, extending in fields ranging from telecommunications to medical technology. In conclusion, Max Planck's work on the quantization of energy was a monumental turning point in the history of physics. His introduction of Planck's constant and the concept of energy quanta laid the foundation for the development of quantum mechanics, which has since become the dominant framework for understanding the microscopic world. Planck's ideas not only transformed our understanding of light and energy but also revolutionized atomic theory and led to the development of modern technologies that have reshaped the world. His contributions to science and technology continue to have a profound impact. His legacy remains one of the most significant in the history of human knowledge. Through his work, Planck changed the course of physics and opened the door to a new era of scientific discovery.